It shows live for me at least.
Yeah. Okay, go for it.
Okay, so fifth talk of the series. We're almost the halfway point. We have Ronald Clark today, and he's a research fellow at Imperial College London, and his main work is in 3D vision and machine learning. He's also an he's a Imperial College Early Career Fellowship holder, and yeah, he did his PhD at the University of Oxford. And he's also received many awards, including a Best Paper Honourable Mention at CPR 2018. So over to Ronnie.
Thanks, Krishna. So yeah, I'll start right away with the talk. So today I'm going to be covering some of the work that we've been doing in representation learning applied to 3D vision problems. So the main things that I'll be covering first is obviously what is representation learning and what do you mean by representations. And then I'll cover a few of the related works that we have been doing in this area. So the first one, so two of them have been published and the other two are still under review, but I'll give you a sneak peek of what they're about in this presentation. So the first one that I'll be covering is ladder, which is an approach for improving variational autoencoders. The second one is deep factors, which is which builds on our CodeSlam work that does dense simultaneous localization and mapping using these learned latent codes. The third one is called Egocentric memory networks, which looks at how we can learn like a memory representation for spatial information. And the last one is a work on estimating human pose with what we call orientation key points. So just to start off with, I'll take a look at what representation learning actually is. So the difficulty of any task depends on how the information is presented. So if we represent a image just as a string of like numbers, and we try to do a task like classify this image as a cat or a dog, then for a human that task would actually be pretty difficult, just looking at this large set of numbers. However, if we compress this or like represent this information in a more intuitive way, for humans this would be in the form of like an image, then it becomes pretty easy to classify whether this image is a cat or a dog. So this is exactly what representation learning tries to achieve. It tries to make it easier to extract useful information from our raw data. And then this can be used for a number of tasks, so in machine learning, this would be, for example, classification, doing some inference, or interpretability or inspecting the characteristics of the data. So a good representation has a few sort of characteristic traits. So the first one that we want is for the representation to be low dimensional. This just makes inference or manipulating the representation easier. The second is that it should be reusable across tasks. So we don't want to have to repeat data over and over just to perform some task. The third is the representation should be spatially smooth and coherent. So we don't want our output to vary rapidly if our latent representation changes only by a small fraction. Then we also, or something that people try to embody in their representations, is this notion of disentanglement. So that generally means that a certain factor in the latent code corresponds to a certain human interpretable factor. So for example, in MNIST, this would be the maybe the roundness of the digits, or like the whether you have two circles on that digit or not, so like a 0 or 8. And then the last one is the representations usually need to be hierarchical and meaningful to be useful. And this just means that we have some hierarchy or relation between the elements in the latent space. Okay, so variational autoencoders are one of the very popular and very good means of actually learning these representations. So how a variational autoencoder works is basically we have a prior distribution. Then we can sample from this prior distribution and pass these samples through a generation network to produce samples or generate samples that represent our data set. So in order to actually find this latent code that corresponds to a given high dimensional sample, VAEs have this inference network as well, which translates the high dimensional sample into this low dimensional latent space. And using this inference network and generation network, we can both reconstruct samples. So we can find the hidden code corresponding to a specific input, and we can generate new ones simply by sampling from this prior distribution. Okay, so one of the interesting applications that we worked on using these low dimensional representations from VAEs is CodeSlam. So in CodeSlam, what we tried to do was to optimize jointly for both the depth and the pose of a stream of input images. So given these two input images, a live image and a reference image, we try to optimize for both the relative translation translation and rotation between them, as well as the depth of the keyframe. So obviously this depth is a very high dimensional variable, having h by w depth variables, and optimization therefore is quite difficult because of problems with dimensionality and also the conditioning of the optimization. So what we did in CodeSlam was basically parameterize this depth variable using the low dimensional latent code from a variational autoencoder. And then in order to optimize for the depth and the pose, we basically just optimize over this low dimensional code that comes from the VAE's latent space. And this allows us to sort of faithfully and accurately reconstruct the depth image just from these monocular inputs. This is an example of the CodeSlam optimization process. We have this live image on the top left. We have the reference image and in the bottom left, and then our optimization process basically perturbs this latent code until the warped live image matches the reference image, and we've recovered a pretty good representation of the depth. So deep factors basically takes this idea of CodeSlam further. So in deep factors, we are given not only a pair of images, but actually a whole input sequence. And what we want to do is solve for all these depth and pose variables. So again, the pose is represented just by our transformation matrix, and the pose is represented by our transformation, and the depth is represented by these latent codes. And in deep factors, we actually introduce or use 3 different factors in our factor graph estimation, and then optimize all these variables using Liebenberg mock-ups. So the 3 factors which we use in deep factors is a photometric factor, which is the same one as in CodeSlam, where we just take the reprojection of the RGB values from the one image to the other, and then take the L2 difference. The second factor is our so-called reprojection factor, which is basically just the geometric reprojection of the 2 points in the image. And then the final factor which we use is the sparse geometric factor, which is the basically the reprojection of the depth in the one image to the depth in the second image in this image pair, and then we take the L2 difference between these geometric quantities. So this is an example of how deep factors works on some scannet sequences. So the system initializes just from a single monocular frame, and then is able to start building this factor graph of frames. And then our optimization is done like on the fly. So we just run in the backend this factor graph optimization, which reduces the error and enforces the consistency of all these factors that we inserted into the graph. Here's an example of some rotational only motion. So our system, the prior is built into this latent code, helps us to cope with these rotation only and other degenerate motions.
Are you able to close loops here?
So we do have loop closures, and we actually add those into the factor graph itself. So the loop closure is done using sparse features, but it's all done in the factor graph. The actual optimization of the loops. So this is a comparison between the photometric factor only and then all of the factors combined. So you can see the photometric factor only leads to some inconsistency between the geometry. This is an example of like our keyframes. So we can also manually select the keyframes. So here we've selected one keyframe and then just sort of move around that single keyframe. And we can spawn new ones as we go along. So this can be done both manually or automatically using some criteria based on the traverse distance or view overlap. Okay, so yeah, this is just some examples of the actual recovered depth maps, estimated depth maps, and the error. So you can see the depth maps are actually quite they're quite sharp and adhere to the geometry of the scene. Yeah, and then this is just a visualization of the Jacobians of the of the depth with respect to the code elements. And you can see that the code actually sort of disentangles this semantic elements. Yeah, so like certain codes would represent perturbations on the table in front here, and certain ones represent the like a perturbation on the chairs at the back and the wall and so forth. Okay, so in Deep Factors and CodeSlam, we saw that you can actually use a variational autoencoder or the latent space from a variational autoencoder to help with these optimization and SLAM tasks. But the standard variational autoencoder has a bit of an issue with faithfully encoding data in this latent space. And the problem basically arises because the prior distribution used for variational autoencoders, like we did in CodeSlam and Deep Factors, is often very simplistic. So people generally just use a Gaussian prior or maybe a Gaussian mixture model, and this doesn't really represent the true data distribution that we're trying to model. So what we proposed in this work, which we called Ladder, is a generative prior model. So instead of using a simple Gaussian prior, we introduced the second VAE, which we used to model the prior distribution of the inner VAE, of the outer VAE. So how it works basically is this generative prior gets inserted between the latent space of the latent space of the outer VAE And we have the inference model producing a latent code, and then this generative prior that compresses it further to even lower dimensional space. And then the generative prior itself has a very flexible hyperprior. So we just used a non-parametric Gaussian mixture for the prior of this generative prior. And this results in some very nice properties. So ladder improves the representation quite a bit. The elbow, so the evidence lower bound, is improved. There's better generation quality, lower reconstruction error. And we also, in this work, showed how we can use this learned data distribution for performing a latent space interpolation task with more faithful generated elements. So this is an example of how the learned prior distribution, or our generative prior, can actually fit the data quite faithfully. So in this experiment here, we just learn a VAE with a 2D latent space with a standard Gaussian prior for MNIST. Then we visualize at the bottom there, or in the first element, the aggregate posterior, which we use as an approximate sort of representation of our true data distribution. So it's basically all the elements in our data embedded into this 2D latent space. And then we learn different prior models using the priors of these different approaches. So the ones we compared to was hierarchical prior. This is one of the other VAE works, GMM prior, the VAMP prior, and then our ladder model. And then as you can see, the Gaussian prior and the hierarchical prior, they fail to model the aggregate posterior or data distribution faithfully, because they kind of completely overly smooth the distribution. The same with the Gaussian mixture model. It doesn't really represent our data because the learned prior is a bit smooth. And VAMP prior does a bit better, but it still has these artifacts which aren't really characteristic of our data. And then finally, ours, you can see, quite faithfully fits the data distribution.
So Ronnie, one problem is that we can't see the key part of that slide because you're in the way.
Yeah. So
I bet you had some magic tool that could shift you to the.
There you go.
Yes. So that is our result. And as you can see, it quite faithfully models the original data distribution on the left there.
Great, thanks.
So yeah, so this next example is just a interpolation task. So in this task, we kind of are given some input, in this case, a 7-digit, and then we want to generate samples or interpolate between samples until we reach this target digit. So traditional approaches basically do this by using a shortest path interpolation. So they just take a linear path from the start to the target, and then output the samples along this path. So what we did was we decided that actually good samples generated from an interpolation should have a high likelihood in this data distribution, because then we would get samples that actually look pretty high quality. So what we did was we formulated this optimization task that includes both the length of the path as well as the likelihood of the steps along this path. And then by optimizing this objective, we get paths which look quite a bit different to the just the shortest length interpolation. And as you can see, these tend to step over the low likelihood regions. And what this means is that so as we traverse along this path, we only generate samples which have realistic sort of outputs. So you can see at the bottom there, the top row shows our shortest likely path in interpolation, and the bottom row shows the shortest path interpolation. And the red square highlights two examples which are particularly problematic, for the interpolation, because they sort of in between the two digits. So the shortest path in the first example generates this weird 3 shape, which doesn't really look like a digit, but ours adheres to nice 7 and 1 digits, and then the same for the middle, where it goes from like a 7 to 8 to 5. Okay, and then this last example is just is also the interpolation task, but on more complex data. So here it's just interpolating between 2 faces of different genders, races, hair lengths, for example, and so the shortest likely path interpolation in this ladder latent space actually produces sort of more realistic images as we interpolate between these two faces. So again, that's just an example of some the faces which usually have some difficulty because they lie in this like low likelihood region in the latent space. But our interpolation method can only pick samples which have a high likelihood, so these faces all look more realistic. Okay, so we've looked at sort of learning representations for data, but in the next work I'm going to take a sort of a bit of a step back and actually say, how can we design a good representation? So in this work, we looked at how we can design a representation for estimating human pose in 3D. So what we want to do is estimate the full skeletal pose of a person in an image using only monocular input. And what we looked at in this work is sort of an explicit representation. So what we did was we actually designed this representation that we need for representing the 6-stop pose for each bone on the skeleton. And this work was kind of inspired by mocap systems, or the way they place these markers all across the body to parameterize the pose of the bones. So what we did was we introduced these orientation key points. So just to demonstrate how these key points differ from traditional human pose and mocap systems. In this slide, I've just put visualized both the key points as well as the actual sort of joint positions that we would infer from these key points. So in the mocap example on the left, you can see that the mocap systems actually kind of over-parameterize the joints or the points that they track, so that they can estimate the full 6-stop pose of all the joints. Whereas normal monocular human pose prediction methods based on joint key points like open pose only predict the joint positions corresponding to the actual joint locations. And what this means is that they can't infer the role of the bone or one of the axes of the bones. They can only produce like this stick figure in 3D. So in our orientation key points work, we introduced extra key points, so extra virtual key points that can actually be used to estimate the full orientation and translation of each bone. So on the right hand side there, you can see that we placed these orientation key points specifically so that we can estimate the full rotation. So taking a closer look at where these orientation key points are actually placed. So this figure just shows 3 bones along the arm, for example. And what we do is we place the orientation key points in the midpoint between the two joints, so joint key points corresponding to a bone. And we place these at different distances from the center of the bone. And then using the estimated positions of these orientation key points, we can just do an SVD and recover the orientation of the bone itself. So this is an example of it working on a actual RGB input. So so all the orientation key points are predicted in 3D from this RGB input. Then using the groups of the key points, we so do an SVD, recover both the center and the orientation of each of these bones. And then finally, we can just fit this full skeleton to these bone centers and orientations. And that allows us to like recover the full skeletal pose. Okay, so then applying this to some of the standard benchmarks. So this is the 3D HP data set. So we obtain pretty good results that outperforms most of the existing methods. And we also obtain pretty good generalization. So even without training on this data set, we get pretty competitive accuracies. And this is an example of the system applied to completely in the wild images. So this hasn't been trained at all on, on tennis videos or any of these videos that we've taken from YouTube, but it still performs pretty good in terms of estimating the poses of these individuals. So for these, for the slow motion videos, we've just like smoothed the joint points over like 5 frames just to make it more visually appealing for the video.
Sorry if you mentioned this, but is it running at real time?
Yep. So this can actually run at about like 160 frames per second on a 2080, and it can run on real time on a device as well, like an iPhone.
So there seems to be a question on the YouTube stream just about this post. So yeah, I think it's Mehdi who has this question. Can we say that you're computing inverse kinematic models and then calculating joint coordinates?
Yeah, so that's actually a very good question. So this is computing the bone positions and orientations themselves. So this is more of a forward kinematic computation. But obviously, if we do that, the bones don't completely align. So there are instances where they are a bit offset because of the inaccuracy of the estimations of the orientation key points. So using an inverse kinematics model, we can actually further optimize it to obtain even better poses. Yeah, so that's so in the paper we haven't done the inverse kinematics model, but that is possible to improve it even further.
Thanks.
Yeah, so yeah, that was the so the orientation key points. So then just the final thing that I want to look at is like how we can actually embed these different representations of our data into a larger memory that can then be used by by an agent or a device to actually do inference about what's around it. So memory is kind of an essential, thing for intelligence, and lots of work in machine learning and deep learning has actually been dedicated to memory. So there's, for example, LSTMs, there's neural Turing machines, and there's memory networks, and all these approaches basically work by in a similar way. They receive some input, they have this dedicated memory, and then they perform both writes and reads of this memory to produce their predictions. And the characteristic of all those existing memory approaches is kind of like that the memory itself and the read-write operations are completely sort of general or uninformative. So they just, for example, a vector that gets inserted in this memory and then read out again when it needs to. However, in many robotics applications, spatial memory is actually what is more important. So an example of spatial memory is, or in its simplest form, would be a map. So this is just from the Facebook's data set with just accurate reconstructions of the spaces. But what we kind of want to do is we want to embed or use this spatial inductive bias in our memory module to help robotics or autonomous applications. Okay, so here's just an example of a spatial of what a spatial memory would look like. So this is from the Fusion++ paper. But what we see is that there's basically objects in the scene, and as we traverse around it, we keep a memory of like where these objects are placed in our map and what the relations are between them. So if we want to sort of learn a memory for general neural networks, we want to use this inductive bias, or we want to use this prior knowledge about geometry, about motion, to actually help our memory to structure these spatial relations. And the existing memory modules like LSTM and neural Turing machines are not very good at this, because they take this general or completely uninformative view of memory. So what we've done in this egocentric memory networks paper is basically we proposed a memory module that makes use of these spatial inductive biases, as well as geometric information to create and keep this memory that moves with an agent. So what this memory is represented as is just an egosphere that encompasses this agent, and it enables like a long-term expressive representation or belief for the agent that stores what exactly is around it. So this memory, egocentric spatial memory network doesn't have general read and writes like the LSTMs and neural Turing machine, but instead uses geometric reads and writes. So the writes all have projective operations, and the reads basically sample or just read from this 3D spatial memory. So how this egocentric spatial memory works is we basically so we have two streams. We have one stream which is the observations coming in, and this is just our RGBD data, so RGBD frames, for example. And then what we do is using the pose and the depth data, we warp these observations into an egosphere. So that's just a panorama or a 360 image that surrounds this agent. And then we quantize it to pixels, and then we fuse it with a past belief. So the past belief is represented by this bottom stream. So what that basically is, it's the past. So the memory at the previous time step, that is propagated forward using the motion of this agent. So we would start with a 360 memory or belief, warp it to using the transformation between the current past and the current frame, and then fuse this with the current observations to update this this egosphere or this egocentric spatial memory around the agent. And so we basically demonstrated the usefulness of this representation on two tasks. So the first one was a drone reacher task, and the second is a manipulator reacher task. And this is basically just two agents, so a drone and a manipulator, and they have to reach this object of interest. And then we used three different setups for the camera. So the first one was with the camera attached to the agent itself. The second one is the camera somewhere fixed in the scene. And the third is the camera moving around in the scene. And so these are just the numerical results for showing the performance on these tasks. So we compared to just a standard CNN, which is mono in that table, LSTM, a neural Turing machine, and then our egocentric memory network. And as you can see, our egocentric memory outperforms all the other models on these tasks. And we've made sort of like, we've taken care in ensuring that all the models that we tested here have the same number of parameters. So we don't have sort of, models, or we're not comparing models with different number of parameters and capacities. And the interesting thing as well, so the ESMN is a variant of our network where we don't store RGB values in our memory, but we actually store features that are learned to best perform this task. And yeah, as expected, this actually outperforms the ESM with just RGB features by quite a significant margin, especially on the first task. So this is a demo of it in operation. So this is just this is an example on ScanNet, and that is just the first frame that's been projected into 3D. And what you see on the left here is the egocentric memory. So that's this 360 panorama centered on the agent. The middle one is the depth stored in this egocentric memory, and the bottom is the current input frame. And then on the right is the reprojection of this egocentric memory into Euclidean space. So you can see as the object or the agent moves around the scene, it builds a more and more complete sort of map or memory of this environment. And the key advantage actually of this sort of or motivation of this approach as well is that for many tasks like the sort of manipulated task or drone navigation task, you basically care more about what is close to you or what is in your immediate vicinity than what is far away from you. So as the agent moves around the scene, you basically can sort of start forgetting what you've seen in the past, and only keep what is exactly relevant for your task at hand, because that reduces the the need for storing all this data. It has many advantages in terms of like attention or focusing only on what you're trying to do as well. So that's what actually allows this representation to improve the performance on those tasks that we tested.
Can I throw in a question?
Yeah. Yes.
Hey, really incredible work. I have a question for the ESMN. Actually, a handful of questions, if I may. I'm sorry. So what's the data that's required for training this? You need RGB, you need depth. Do you also need IMU or the odometry?
Yeah, so what we need for the training is just the RGBD images, and then we also need the pose.
Right.
So that
Like
can
ground
be
truth pose.
odometry or SLAM or some. So for the manipulator example, we actually obtained it from the actual device itself. So there are encoders, position encoders, and orientation encoders in the device.
Right.
So yeah.
Okay. Then how is this trained? Like, is this like? Sorry, let me rephrase this. Is this trained in such a way that you have zero-shot generalization, that like you learn a general like warp and update function, so that in any new environment you can fit it like on the fly, or is this like fitted to a single environment?
Yeah. So for the actual tasks that we tested on, so for the drone reacher task and the manipulator reacher task, those are trained on a range of scenes and a range of like, example targets and starting positions. So it does generalize to different environments and different conditions. For the untrained variant, so if you're just using it to actually build this this map, but you're not specifically using it to perform some task, then you can actually get away with just training. So the RGBD variant you can actually run without any training, because it'll just build this egosphere or this egocentric map just from the RGB data and the pose. But obviously the interesting thing comes in when we actually train those features for the task at hand or for some specific purpose.
Okay,
so
cool.
Yeah.
And then two more, if I may. If anybody else has other burning questions, please interrupt me. So you showed us how the write operation works, where you like in the like where you have those two streams, and then like you're merged, so you're fusing those and like writing them. Yeah, exactly, and then writing them into your past memories. How does the read play in here? Because you made that analogy to the neural Turing machine.
So the read, so for the task that we had in this example, the read was basically just a dense operation on the memory itself. So we had convolution acting on this egocentric representation. So in our example, it's just a 360 image, which is represented as a EP rectangular 2D image, and then we just use that as input to the next part of the model. So in the drone reacher and the manipulator tasks, it's basically like we have this egocentric memory model or module, and then that output, which is just that 2D map, gets fed into the next component, which is the policy module.
Okay, and this is all trained end to end.
Yes, yeah.
Okay.
So basically the error gets propagated through the whole thing, and then the features that that are stored in this memory module are learned to best perform the task.
Right. Very cool. And last question. You mentioned at the beginning of this section, the ESMN section, that there is a lot of geometric bias added here. And I saw like here you mentioned like this warp, like this projection from image space to this like panoramic space. And in the bottom row here, also in this diagram, you have this like geometric bias that is the transformation from one pose to the next pose. Are there any other geometric features in here or biases, or is that it?
No, so it's mainly the root projection, which uses the motion, plus the 3D the multiple geometry, which is used to actually do the root projection itself. So basically projecting it out of the one so the memory at the one time step, and then reprojecting it back into the next time step. Plus the the projection from the actual observation into this memory.
I have a somewhat related question. Like,
Thanks.
do you like what's really the idea between or the motivation behind having an egosphere as the representation, like over, let's say, alternative parameterizations? Could you shed some light on that?
Yeah. So the main like sort of the motivation of it initially was actually that sort of this observation that if you're performing a task, the immediate data that you are operating on, or the immediate observations, is just what you're seeing from your current viewpoint. So it's kind of like if you're doing any task, you probably the current action that you're taking will be from your current your current point of view. So we kind of wanted to mimic that sort of like biological type of working, and that obviously has the benefits of like reducing the storage space because we don't have to like keep this huge dense map, and it can also, like I said, like focus the attention of this map on the specific immediate vicinity around the agent. And then the disadvantages aren't that much because we don't lose any information in doing this, mainly because we can learn those features through the actual network. So because obviously one of the potential disadvantages of keeping a map that is constantly updating based on your pose is that you do lose information from the past to some extent. But then for these tasks that we tested along with the learning of these features, we didn't really observe any degradation in performance or anything like. So actually from these examples we can sort of see that this egocentric map representation is pretty useful or ideal for these types of reinforcement learning tasks.
Yeah, thanks. And what do you think it would take for solving non-local tasks, like tasks where the goal is actually far off from the current view? Do you think you can still learn that in a somewhat similar framework?
Yes. So I think if it's some, maybe some maze navigation or, like large scale maze navigation, or like something where you have a much larger scale map or geometric information that you have to work with, then building having a sort of a more explicit global representation might be useful. Just because in this egosphere representation, the network will have to remember, those global details in the features that it stores, in this egosphere. So I think in cases like that, it would probably be beneficial to keep some, like global memory unit as well. But I think for most tasks like navigation or, those tasks, you can sort of separate the global, the global navigation from the local, because to navigate, if you're navigating, you kind of just do, kind of local obstacle avoidance, local tasks like opening doors and stuff. But then the global planning is kind of a separate thing.
Yeah, possibly tasks like global localization are better handled by.
But I actually, we haven't actually tested that, so I think it'll be quite interesting to see how this performs on large scale maps or navigation as well.
Makes sense.
Yeah.
Thanks.
So I guess you're finished the regular part of your talk, so we should say like Thank you.
Yes.
I guess we just like dove right into the question part, which is okay, which is great. There was a question from the YouTube going back to the previous work on the 60, like the human pose estimation. So I'll just read it out. So the question is the training image, is the training image very different from the YouTube video sequences that you showed? And do you take special care with the domain shift, I guess, between the training data and the testing data?
Yes. So the domain is quite different because those models are all trained on like human 3.6 M and I think it's MPII. So those are kind of like these motion capture, studio setups. And then obviously those YouTube examples are outdoors, completely, different camera and everything. So generalizes extremely well. There is just some, there is some care that has to be taken when testing on different data sets though, because the skeletons differ. So, a human 3.6 M has a different size, size skeleton and different bone ratios and stuff. So there's a little bit of like retargeting that has to be done if you apply it to a different skeleton. But obviously for testing, that's not really relevant because you can just use you can kind of use the same skeleton that you had, or you can estimate the skeleton actually from the predicted key points. So what we did for the testing was actually take so because our orientation key points and joint key points are just predicted in 3D, we can actually estimate the bone lengths from those key points. So we just took the average of each bone length across the entire sequence, and then used that to create the skeleton. And then we just mapped those orientations and poses onto that skeleton.
Cool. I also had a question going back to the start. So I remember reading the CodeSlam paper a while back, but I sort of forget the details. You know how it is. But you've chosen to represent the depth as the latent code. And then, for example, in the deep factors work, you're still building sort of these factors over the RGB like photometric properties.
Yes.
So there's this choice that like depth should be represented as latent codes, but we should keep RGB image like information as it is in some sense, and not like encode it. Is that so? A, do I understand things correctly? And B, like, is that the only way that it could be, or could you see doing it another way?
Yes. So that's actually an interesting point. So the depth is the quantity that's encoded, because those are actually the variables that we're optimizing. The RGB doesn't have to be encoded because we're not trying to recover the RGB. We already have it.
Yeah.
But we are using the RGB obviously for the actual error or the residual computation. But like that can be done directly from the RGB itself. There are actually cases where it might be beneficial to encode the RGB as well, because obviously if you have two frames and they don't exactly overlap, so there is some missing information. So like having a autoencoder on the RGB could help to complete the one image as you're optimizing, kind of like simultaneous kind of image inpainting plus depth and pose.
Right.
But that's not exactly what we're doing.
And in this deep factors work, like those factors looked a little bit nasty. Like, is this optimization nice in practice? And like, what about, you mentioned something briefly about relinearization. Is that like something that you have to do really, really often to make sure that you're not in a local minimum? And like in practice, how does this really work? Like, do you have to pay very careful attention to the trajectory that you take with the camera so that you don't diverge and stuff?
Yeah, so the trajectory isn't, so it works with pretty much, quite difficult trajectories. Like the example there with the rotation only and like going kind of close and far from all these objects. The relinearization, it wasn't that frequent. So I think we did it every time we take a new keyframe in this sequence. But yeah, there are still, I would say the major issues with it at the moment is just the actual representation from the autoencoder, because sometimes it doesn't like sometimes it favors some weird shapes, so and it's not really that easy to sort of like diagnose what is happening. For example, lots of times it kind of like imagines it's random or like the wall and the ceiling or the wall and the floor are kind of like inverted, and the other way around. And so like degeneracies like that, it doesn't completely take care of. But I think the main way to improve that would actually be to improve the autoencoder, or to improve the representation that's learned. Because at the moment as well, like for deep factors and cosine, we haven't really optimized that representation. Like we haven't optimized it for the SLAM task. Kind of, we've just done this autoencoding and then hope that that representation actually works well. So I think there can be some like optimization and innovation done there.
So is it true that like, so in a normal like factor graph setup, you would like write out these factors and like you would have some kind of idea of what the optimization landscape might look like, and you could control it with cost functions and things like that.
Yeah.
But is it now the case that because you've added this other learned element that it becomes like even more difficult to sort of reconcile how this already complicated nonlinear optimization is now jiving with this other relatively like kind of opaque like learned representation?
Yes, so like there is the extra sort of element of like what the network is actually predicting as well, because we can sort of like visualize it with visualizing these Jacobians and sensitivities, but it doesn't really give us the sense of what the optimization process is doing with those values. So it does, because we did sort of like struggle with it a bit in terms of like thinking, how can we improve this? Like, do we have to train this network on like some extremely large data set, high quality data set, or do we have to improve the optimization, maybe switch to some more complex optimizer or robust optimizer? And we haven't really got an exact or good answer for that yet.
Interesting.
The one thing as well is like it depends quite a bit on so we have these prior factors that we predict directly from the image. So basically in this okay, I haven't shown it there, but like in the setup we have both the pairwise factors between the two each pair of images, as well as this prior factor which comes from basically just a monocular depth prediction. And if we obviously if we get really good monocular depth predictions from this prior network, then we can actually the optimization works a lot better.
Yeah, it's like getting a really good initialization point for every single
exactly thing. Yeah. So in this case, we haven't used it as an initialization, we've just used it as like a prior or like a constraint, which also helps a lot compared to like the CoSLAM model.
Yeah, so but hopefully it's acting like an initialization in the nonlinear optimization process, like putting you in the basin of convergence and not in some, like you were describing, some like alternate possible like degenerate case or something.
Yes, yeah. So it was actually in most of the cases where the, sort of like walls and stuff inverted, that was lots of times a result of like the prior predicting, random things.
Right. Very cool. So I don't know. I don't have any more questions. I don't want to be cognizant of your time. But does anyone else have other thoughts? This is all very, very impressive, cool work.
Thanks.
Okay, so I guess just since we are about 5 minutes over time, let's just thank the speaker again, and thanks Ronnie for like accepting the invite and talking to us.